All right, then thank you first of all for the introduction. My name is Andrej. I am from Kiel University, of the chair of Professor Höher. And my colleague Sunil here and I have been working on this topic together. Normally I am from the optical communication perspective, or I work in optical communications, and my colleague Sunil here works on molecular communications, and this work is the result of our both topics combined, which is detection process and macroscopic air-based molecular communications using a PIN photodiode. First of all, some introduction. This has been done before. This is the state of the art. The work that we have done before, you've seen this in the presentation before. This was this large tube, a 2-meter tube, and we achieved molecular communication of up to a distance of 1.8 meters. And for that, we use a fluorescent dye and a sprayer as a transmitter, and typically a camera as a receiver. The general motivation is that the data rate for molecular communications is much lower than, for example, compared to optical communications or radio communications. And specifically for this work, we wanted to upgrade our testbed in order to push the boundaries of the data rate while maintaining a low bit error rate, and also use information carriers which are less harmful to the environment. A small outline. First, I will show you the testbed again and explain the differences. Then I will show you the transmitter briefly, then introduce the novel receiver that we apply, and talk about the results, and conclude my talk afterwards. So this is the picture that you've seen before. We have on the left-hand side the pressure sprayer and a controllable valve that sits over here, and a microcontroller that controls this system. We have a channel, it's a 2-meter tube, which has flaps over here, and also on the other side, so 3 times 6 flaps with a distance of 30 centimeters to increase the distance. And on the receiver side, typically we have a camera that sits on top of the flaps and a UV light over here, UVA light, which excites the fluorescent dye. The camera records with 480 frames per second, and afterwards video post-processing is done. Again, this is the state of the art with the blue parts, and the new part for today's talk. First of all, we used a new valve, a solenoid valve, a faster one. We now changed to a highlighter ink solution, which is water-based. And for the receiver, we dismissed the camera and put as a new receiver a photodiode and a oscilloscope with 12.5 kilohertz sampling rate, because the time scale is quite large, and also some offset and noise removal parts. First up, the transmitter. It's a 12-volt solenoid valve, which is controlled by a microcontroller and has a maximum tolerance pressure of 10 bar. The new one that we're using has a shutting time of 10 milliseconds. The previous one that we used has a shutting time of 30 milliseconds, which means it's 3 times faster. And faster in this case means that the transition between on and off is faster. This means that for an off keying between 1 and 0, the decay is a lot faster. For the information carrier, we switched to Adin 345. It's a highlighter ink. It's a water-based solution that you can add to water. When excited by UVA light, which you can see over here, at 398 nanometers, it produces this this emission with peak emission at about 600 nanometers, and it's a safer alternative. Previously we used rhodamine 6G, and now we use Adin 345, which is also used for experiments in blood vessels. The concentration is typically measured in milliliter per 3 liter, was optimized in our case for 60 milliliters per 3 liter for a distance at 88 centimeters. This was done in an experiment where we had the camera and especially looked at the red pixel energy and the concentration where the previous, so the rhodamine and the Adin, where the intensity matched. was at 60 milliliters. And also, of course, you could add more and more and more highlighter ink into the water, which would increase the fluorescence, but of course we have a limited availability, so this was, first of all, to ensure a fair comparison, and second, because we have limited access. Now to the detector. Previously it was a camera-based version, now we switched to a photodiode-based version, especially a Hamamatsu large area photodiode, which has 1 square centimeter of photosensitive area, so quite large. Some have a square millimeter range, because we need to detect a lot of light, because the fluorescence is quite small, the intensity is quite small. Now a photodiode produces, when excited with light, produces a current, which is proportional to the intensity. And what we need to do is, first of all, we need to amplify, because the intensity is really, really low. And second, we want a voltage at the output. This means we can simply use a transimpedance amplifier. The current flows through the resistance over here, and the resistance acts as the amplification part. This means, because the signal is so weak, we need a really, really large amplification. Therefore, we have feedback resistance in the mega-ohm region. So this one produces a current. We amplify the signal, and then at the end we get a voltage at the output. This is what the PCB board looks like. As you can see over here, the detector is really large. And what else do we need? We need an optical filter. The reason for this optical filter is that any sort of light gets amplified at this part. This means also the UVA light, which excites the fluorescent dye, would also get amplified, which would cause the detector to saturate. If you're interested in why this is the case, I can explain later on, but this is definitely required. And this filter produces this filter curve, which means that the UVA part is nearly completely cancelled out, and our interesting part with the fluorescent dye, a little bit of attenuation, it's about 92% of transmission, is kept, and we can then use it and detect it. Okay, so now the dye is sprayed through the pipe, it is detected, it's converted into a voltage and amplified, and now we're looking at the post-processing step. First of all, the reason, again, why the oscilloscope samples only at 12.5 kilohertz is because we have a large time scale. It's about 10 seconds that we were recording. But comparing the 12.5 kilohertz to the 480 frames per second, this is still really good. When also, of course, to reduce the noise, we applied a 10 kilohertz low pass filter. And when we looked only at the noise, so there wasn't any signal present, we found, when computing the FFT, that there are some peaks. The first one is at 50 Hertz, the second at 150 Hertz, and then in 100 Hertz steps. And those, or the reason that we think that this happens is because the pipe's right next to the power lines. Power lines have 230 volts in Germany at 50 Hertz, and also those peaks, those additional peaks, are probably harmonics. So to get rid of those, an additional 40 Hertz digital low pass filter was applied. Finally, this is the received signal that was recorded with the oscilloscope. Those are sprays with 10 milliseconds shutting time and 200 milliseconds in between. As you can see, really good detection possible. For the results, first of all, we computed, or we looked at the signal to noise ratio for varying distances. So for increased distances, starting at 58 centimeters, right at the front, up to 180 centimeters approximately. And as you can see, first of all, the SNR increases. Afterwards, after 180 centimeters, it decreases again. The reason for the increase is because it has a dispersion. The sprayer, the nozzle, has a dispersion. At the beginning it's quite small, and then at some distance, which is in our case 118 centimeters, it's a cloud, it's quite perfect. And for larger distances, this is probably the gravity which causes the droplets to drop, and therefore the distance to the detector, which sits on top of the pipe, is greater, which means lower intensity, which means lower signal. So a decrease of the signal in this case. Finally, we looked at the bit error rate performance with a fixed threshold detection, also with the oscilloscope for several distances, and we computed those bit error rate values for 20 trials, also for increasing distances. First of all, the orange curve is the benchmark. This was previously done for a shutting time of 20 milliseconds. And as you can see, it's quite good, sometimes even with no errors. When we compare it, however, to the photodiode-based curve, we can see, first of all, this is a shutting time of 10 milliseconds, so half of the duration, and still better. If we compare it to the camera-based detection, again, also with 10 milliseconds, we are over here. So the photodiode-based version is a lot better in this case. As a conclusion, first of all, we successfully upgraded our testbed. To achieve higher data rates, we applied a faster switching solenoid valve. We changed the detector to a PIN Photodiode-based detector, and we use a safer information carrier with adding highlighting. Therefore, we achieved a transmission rate of 50 bits per second over a distance of 1.8 meters, which is perhaps the fastest achieving multiplayer communication so far. For the outlook, first of all, it would be interesting to do an end-to-end model considering the photodiode, and of course you could do different things with different colors, for example, by applying different optical filters, for instance, and do also multiple input and multiple output communication, for example, with different colors. Yes, thank you for your attention. Are there any questions?
Thank you, Andrej. Any questions?
So maybe I'll start.
Yeah.
Did you observe any saturation effects in the channel? Because I assume when you're spraying in them, you have like an opening angle, and the outermost parts of your spray would then hit the tubes. So if you run it for like a longer time, like say an hour or so, do you have some residual liquid on the walls of the tube?
First of all, we wouldn't be able to run it for an hour because of the pressure sprayer. And secondly, this is also one reason why it decreased, because of course particles hit the wall and not all this.
Okay.
But the detector itself, I think the field of view is not far enough to hit the walls.
Okay, because then I would, if you're interested, we developed a different mechanism for creating that spray that is just using a so-called ultrasonic mister. And with those, you more or less don't have a direction. So it just really evaporates, and if you then have some kind of flow that pulls it through the channel, then you might not have these outermost droplets that you really spray. And this might help you. If you're interested, we can talk later, because we already have everything needed, and I can send it to you if you want.
Can you maybe say what distances you could achieve with it?
We have a test bed in Linz where we transmit over distances of 1.50 meters or so. And so approximately that distance, and it would for sure work even further than that. But this is currently the setup. I also have some pictures. If you want me to, I can show you later.
Yeah, certainly. Thank you.
Sure.
Next question.
Yeah, going more in the direction of your outlook. I remember from previous discussions, I mean, you just mentioned it already, that you have problems with your pressure decaying over time. So, like, what is your current transmission time limit with your high data rate? And do you have any plans on solving, I mean, besides from Stefan's solution, on solving your pressure decaying in your pump?
I'm not really sure about long periods because we just simply do some measurements, then increase the pressure again to 3 bars. It's constant. I'm not really sure about any long-term effects.
Okay. And then a second question. Also, you briefly mentioned that you're thinking about maybe multiple colors. So how concrete are you getting? Are you going to start like with 2 or more? Have you thought about, are you going to have like an array of multiple photodiodes and filters, or use something like a spectral sensor?
Yeah, spectral sensors probably not fast enough. So first of all, I would try this with an array of detectors that have optical filters in front of them. The problem is, however, that you can't just take 1 million colors because obviously they are right next to each other, and this spectra are quite wide. So I would guess or suggest, because also this region over here is because of the light, it's not accessible. I would just try it with 4 colors. Yeah.
Great.
And the closer they are together, of course, the higher the eyesight, the better the optical filters should be. Yeah.
Any other questions? Okay. Thank you, Andrej. Thanks a lot.